Hello everyone, I'm Gautam from CSE department. Today I'll be presenting on the traveling system problem. In short, it is known as TSP, one of the most famous optimization challenges. We'll explore its applications in real-world chains like Amazon and Uber, who use similar principles to optimize their logistics and ride-sharing routes. What is traveling salesman problem? The traveling salesman problem is a classic optimization problem used in computer science, mathematics, and operations research fields. It is a classic problem in optimization, where a salesman has to visit a set of cities each exactly once and then need to return to the starting point while aiming for the shortest possible route. The traveling salesman problem is crucial for optimizing the routes in logistics and transportation, significantly impacting cost efficiency and service delivery in many companies and organizations. Now let's compare the traveling salesman problem with Hamiltonian cycle problem. The travel salesman program majorly focuses on cost minimization, such as finding the shortest path, but the Hamiltonian cycle only seeks to determine the cycle visiting all vertices exists without worrying about the distance. This makes the traveling salesman problem particularly challenging and computationally intensive. Let's have a look into the NPR nature of traveling salesman problem. Traveling salesman problem is an NPR problem. As the number of cities grows, the required calculations increase exponentially. This makes exact solutions impractical for large datasets, which is why companies often use approximate methods to get good enough solutions. Now let's have a look about some of the real-world applications of traveling system problem. The first one is logistics and delivery operations. Companies like Amazon and Uber use traveling system problem to optimize delivery rates. Their goal is to minimize delivery time and fuel costs by finding the shortest possible routes that allow delivery to reach multiple destinations efficiently. It significantly improves the delivery efficiency, reduces operational costs, allows the environmental impact by cutting down on fuel consumption. The next application is ride sharing and route planning. Uber, Lyft, and other ride sharing services use traveling system principles to determine the best pickup and drop off sequences for multiple passengers. The goal is to minimize the delivery travel time for the driver and reduce waiting time for the passengers, especially when multiple pickups are requested. It significantly enhances the customer experience with shorter wait times, reduces fuel usage, and increases driver efficiency. The third application is printed circuit board manufacturing. In electronics, traveling system problem help determine the shortest path for drill heads in PCB manufacturing, which have to drill multiple holes. The goal is to minimize the movement of the drill head to save time and increase the production speed. Thus, it reduces the manufacturing time, increases the productivity, and lowers the damage and wear on machinery. The fourth one is one of the major applications in drone delivery and autonomous vehicles, which is relevant in today's world. Delivery drones and autonomous vehicles use traffic system problems to calculate optimal delivery routes. The goal is to maximize coverage efficiency, especially for multi-stop routes, while minimizing battery usage. It results in extended battery life, improves delivery efficiency, and aids in real-time route adjustments in case of any obstacles. Now let's have a look into Amazon's route optimization strategies. The first strategy is strengthen technology. Amazon's advanced algorithm and machine learning capabilities enhance route efficiency, leading to significant cost savings and improved delivery times. The second strategy is weakness in complexity. The intricate nature of route optimization algorithms can lead to challenges in implementation and require substantial computation resources, potentially hindering scalability. The third strategy is opportunities for innovation. Continuous advancements in AI and data analytics present opportunities for Amazon to further refine its logistics strategies and enhance customer satisfaction through faster delivery. The fourth and last strategy is threats from competition. Increasing competition in the e-commerce sector may pressure Amazon to continuously innovate its route optimization strategies to maintain its market leadership and operational efficiency. Uber's dynamic pricing and routing plan, which contains two methods. The first one is surge pricing dynamic. Surge pricing is a critical mechanism that adjusts fares based on real-time demand fluctuations, ensuring that rail availability aligns with the rider. Suppose let's consider the traffic is too high in a particular route, the fares will be significantly higher than the normal fare. Thus, this approach not only maximizes driver participation during peak times but also enhances the overall efficiency of the ride sharing service by prioritizing urgent requests. Algorithmic route optimization. Uber's route optimization employs algorithms like A star, Digistars, and Traveling Salesman Problem and VRP to find the most efficient routes for riders. It factors in real-time traffic, distance, multiple pickups, and dynamic conditions. For services like Uber Pool, it minimizes the total travel time by optimizing routes for multiple riders, ensuring timely and cost-effective transportation while adapting to changing road conditions. Let's have a look into the transition problem C code example. This code calculates the shortest route that visits each location exactly once and then returns to its starting point. It uses dynamic programming and bit masking to improve the efficiency. First, they include the standard libraries for input and output operations. Then we define the number of locations of 5, representing the number of locations or cities in our travel system problem. Next, we define our TSP function. The TSP function will calculate the shortest route that visits every location. This function has four parameters. The first one is distances, which is a 2D array of distances between locations. The second one is force, representing the current location. Visited tracks the locations we have visited using a bitmaps. And the DP array or table to store already computed distances for different routes. So inside the function, we handle the base case. If visited matches the one visited matches this bit shift, it means all locations have been visited. The function then returns the distance from current position goes back to the starting location 0, completing the round trip. Next, we check if the subproblem has already been solved by looking into the DPT. If the if the DP of person visited is not 1, that means we have computed the shortest route from the current location with a given set of visited cities. Then we simply return the saved result to avoid redundant computation. So now we calculate the minimum distance for visiting all locations from our current position. First, we set the min dist to high value in max to ensure it's updated with the actual minimum distance. Then we loop through all the locations with log. If a location hasn't been visited yet, then we calculate distance from post to log plus the result of the recursive call to TSP function for next location. Each time we update the min dist with the shortest route found for this configuration of cities. This recursive call allows us to explore all possible routes from the current city, ensuring we find the minimum possible route distance. Finally, we store the min dist for the subproblem in our DP table and return. This ensures that any future calls with the same parameters can quickly retrieve the result from the DP table, reducing the computation time. Let's jump into the main function. In the main function, we define our distance matrices with some parameters which can quickly retrieve the result from DP table, reducing the computation time. This matrix represents the distance between each pair of locations. For example, distance of 0 of 1 is 12. which means the distance from location 0 to 1 is 12. This matrix defines the distances between all pairs of locations. We initialize our DP array to -1. This ensures that every subproblem starts as unsolved, allowing the TSP function to store results here after computation. Finally, we call our TSP function and print the optimal route distance. We start from location 0 and mark it as visited in 1. The TSP function then calculates the shortest possible route that covers all locations and it returns to the sort. So let's run this, execute this program. So here we can see that the optimal route distance is equal to 80. Let's look into the performance analysis of TSP-C program that we had a look into it. The time complexity is big O of n square into 2 power n, where the 2 power n represents all possible subsets of locations and n square account for the nested loops that check every possible route between cities. The implication here is that the complexity is exponential and grows rapidly as the number of cities increases, making it feasible only for relatively small number of locations. That is, it can be up to 20 cities. Next, we have a look into the space complexity. This solution uses dynamic programming with memoization to store previously calculated paths. So the space complexity is also big O of n square into 2 power n because of the dynamic programming table DP. The DP table stores results for each subset of cities. Each starting point is in memory proportional to n into 2 power n. Implication is that this memory requirement can become a limiting factor for systems with constrained resources if n is large. Let's look into some of the alternate approaches to solve traveling system problem. The first one is genetic algorithm, which is inspired by natural selection. Genetic algorithms use a population of possible solutions, applying mutation and crossover to find a near optimal route. The next one is simulated annealing. This technique mimics the process of metal cooling, where a high temperature allows for more exploration, gradually lowering to stabilize on a solution. The next one is ant colony optimization. Based on foraging behavior of ants, the ant colony optimization uses pheromone trails to guide solutions, which frequently use paths reinforcing optimal routes. Why companies use approximate solution, which we have discussed in the comparison with Hamiltonian cycle. One of the major factors is scalability. Unlike exact PS travel system problem solutions, approximate methods can handle thousands of locations in a reasonable time frame. The next factor is flexibility. Approximate methods adjust easily to real-time changes in delivery conditions or traffic, but the traveling exact traveling system problem solution do not do not adjust easily to real-time changes in any other conditions. Next, we have looked into real-world complexity changes. Although traveling system problem-based optimization is powerful, companies face several challenges in real-world applications. Real-time traffic changes require Uber and Amazon to frequently adjust routes to maintain efficiency, especially in cities with unpredictable traffic. Unexpected delays like road closure or adverse weather further complicate planning. Lastly, high computational requirements can be a bottleneck, especially when processing routes for hundreds or thousands of locations. That is why companies use powerful algorithms or technology to manage these demands effectively. The impact of travel system problem solutions in companies like Amazon and Uber is substantial. Reduced delivery times lead to a greater customer satisfaction, giving this company a competitive edge. Additionally, lower operational costs from optimized routing into reduced fuel and labor expenses, improving profitability. An added benefit is the environmental impact. Efficient routes lower carbon emissions, helping these companies contribute to sustainable goals. By balancing the customer needs, cost savings, and environmental impact, travel salesman problem solutions bring significant advantages and changes. Let's visually compare the exact and approximate solutions. The exact solutions are optimal but impractical for large data sets due to exponential growth in computation time, while approximate solutions are slightly suboptimal but much faster and suitable for large data sets. Example comparison is showed in the right side, where we can see both the graphs of exact solution and approximate solution. We can notice that the differences are minimal, but the time savings are really significant. Thank you.